Sorry for interruption. Let us continue. So we're discussing about the solution to this critical section problem, which can be implemented using three code section: entry section, critical section, and remainder section. Now here we have the pseudocode for a process with a critical section. So this is a general structure. While a condition is true, there is entry section, and we know in entry section process requires permission to enter their critical section. If permission granted, then it will enter into the critical section and will execute there. After finishing the execution of critical section, it will enter remainder section, and here is the end of while loop. So this is a general structure of a process with critical section. Now a solution to critical section problem here must satisfy the following three requirements. In order to apply the solution to critical section problem, here we have three requirements that must be satisfied. Number one, mutual exclusion. If a process is executing in its critical section, then no other process can be executing in their critical section. This is called as mutual exclusion. There can be only one process at a time executing in its critical section, and while it is executing in its critical section, no other process is allowed to enter their critical section. This is a condition called as mutual exclusion. Second is progress. If no process is executing in its critical section and there exists some processes that wish to enter their critical section, then only those processes that are not executing in their remainder section can participate in the decision on who will enter its critical section next. See, when there is no process executing in its critical section, first you have to check there is no process executing in their critical section, and there are some processes that are requesting to enter their critical section. Two conditions we are checking here: no process executing in critical section, and there are some processes who are requesting for critical section entry. Then among the requesting processes, we need to again examine that the processes who are requesting to enter their critical section must not be executing their remainder section. Then and only then they can participate. Again, they can only then be the candidates who will be considered for granting permission to enter their critical section next, right? So the selection cannot be postponed indefinitely. While selecting which process will enter the critical section, if it is not executing in the remainder section and there are no processes in the critical section, then the selection will be done, and this selection cannot be postponed for a longer duration. Okay. Third situation here is bounded waiting. So there exists a bound, or we can say there exists a limit on the number of times the other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. Bounded waiting is a situation where we are limiting the processes to the number of times they can enter their critical section after they had made a request and before the request is granted. We assume that each process executes at a non-zero speed. First assumption we are keeping here is the processes executes at a non-zero speed. The speed of execution is non-zero. Okay. Then second assumption is concerning relative speed of n processes. We make no assumption about the relative speed of the n processes here. Next point is protecting kernel code from race condition. Various kernel code processes that perform the following activities must be safeguarded from possible race conditions. Now we are aware of what is race condition. Here, kernel code must be given a protection against a race condition. So there can be processes which perform activities on the kernel code, and we need to safeguard the kernel code from race condition. We can do this by maintaining a common list of open files, updating structures for maintaining memory allocations, then updating structures for maintaining process list, updating structures used in interrupt handling. There are two general approaches to handle critical section in operating system. First one is primitive kernels and second one is non-primitive kernels. Let us have a look at primitive and non-primitive kernels. Primitive kernels allow a process to be preempted while it is running in kernel mode. So primitive kernel, it allows processes to be stopped while it is running in kernel mode. Must be carefully designed. Primitive kernels must be carefully designed to make sure that shared kernel data are free from race condition. Shared kernel data cannot face, we need to avoid a race condition for shared kernel data. So it must be designed carefully. It is suitable for real-time programming. Primitive kernel may be more responsive as it won't be waiting for a kernel mode process to relinquish the CPU, that is processor. And it is implemented in Linux and Solaris operating systems. Whereas primitive kernel does not allow a process to be preempted while it is running in kernel mode. In case of primitive kernel, it does not allow a process to be stopped in between while it is running in kernel mode. Non-primitive kernels allow a process to run until the process does one of the following. So primitive kernel allow a process to run it, to continue with its execution until one of the following is done by the process. This includes exit kernel mode, blocks, or voluntarily gives up the CPU, that is terminates itself. Non-primitive kernels essentially free from race condition on kernel data structure, and it is implemented in Windows XP and traditional Unix operating system. Next point to be discussed is Peterson's solution. It is a classic software-based solution to the critical section problem. Just now we have discussed critical section problem. So this Peterson solution is a classic software-based solution for critical section problem. It provides a good algorithm description for solving the critical section problem. It also illustrates some of the complexities involved in designing software that addresses the three solution requirements. We have discussed it earlier, three solution requirements, that is mutual exclusion, progress, and bounded waiting. Unfortunately, the assembly language implementation in modern computer architecture will not guarantee that Peterson's solution will work. If we are implementing it, if you are implementing assembly language implementation of Peterson's solution then in modern computer architecture, then it will not guarantee that it will provide the solution to critical section problem. Since load and store are not atomic transaction in case of assembly language programming. Now, Peterson's solution is restricted to two processes that alternate execution between their critical section and remainder section. So, Peterson's solution is restricted to only two processes. Now, these two processes alternately switch between their critical section and remainder section. It also assumes that load and store instructions are atomic and they cannot be interrupted in between. The processes are numbered P0 and P1. Here we will be numbering the two processes that are executing alternately between remainder section and critical section as P0 and P1. Now for convenience, let us use a notation Pj for other processes. Other than P0 and P1, if there exists some process, let us call it as Pj. Now j equals to 1 minus I here. Just to make a differentiation, we are using these terms. The processes share two variables. The two processes P0 and P1, they share two variables here. And other than P0 and P1, if there is some process, we are calling it as Pj. These two processes, they are sharing two variables as turn, which is of type integer, and flag, that is of type boolean. So if we are declaring a variable as boolean, it can have only two values, 0 or 1 or true or false. The variable turn indicates whose turn it is to enter the critical section. If turn is equals to I, then process I is allowed to execute in its critical section. In general term, if turn is equals to I can be any integer variable. If I is 1, then it is process P1's turn to enter its critical section. The flag array is used to indicate if a process is ready to enter its critical section. If flag of I is equals to true, then Pi is ready to enter its critical section. I hope you are following. Let us have a look at the algorithm for process P1. Now int, turn, boolean, flag. These are the two variables that we'll be using here. Now here we have a while loop. While the condition is true, while it is true, flag of I is equals to true, indicating that the process is saying that it is ready to enter its critical section. Turn is equals to j indicates that it can go first if it is ready. If turn is equals to j we are using which is 1 minus I. Okay. So if I is equals to 1, j will be 0. So it indicates that it is P0's turn to enter its critical section. While flag of j and turn is equals to j, then you are in your critical section. That means this particular process will be in its critical section and it will execute its critical section. As soon as this process raise the flag, raise its own flag as false, indicates the other process that it has finished executing its critical section, and it enters into remainder section. Here is the end of this while loop. So this is an algorithm for process P1. All this is done for synchronization. Now here we discuss synchronization hardware. There's a concept called as a lock. So in order to do process synchronization, we require an additional hardware. This additional hardware is called as a lock. Just like we put a lock over the door to safeguard our house, so you can consider the same example, but here we are putting it onto critical section. So in general, any solution to critical section problem requires some form of hardware, some form of lock. And race conditions are prevented by requiring that critical region to be protected by locks. A process must acquire a lock before entering its critical section. So it is a liability for a process to gain access to this lock before it enters its critical section. A process releases the lock when it exits from its critical section. So first is the thing, it should acquire a lock, then it should enter in its critical section, execute the critical section. As soon as it finishes the critical section execution, it must release the lock and then enter the remainder section. Many systems provide hardware support for critical section code. In case of single processor, it could disable interrupts. When you have single processor, then this could disable interrupts. Currently running code would execute without permission. Here in case of single processor where the interrupts are disabled, then currently running code would execute without permission and generally too inefficient on multiprocessor system. This mechanism is inefficient over multiprocessor systems. So your operating system using these are not broadly scalable. In modern machines, they provide special atomic hardware instructions. Other than locks, special atomic hardware instructions are provided in modern machines here. An atomic is equals to non-interruptible. This atomic hardware instruction, this is non-interruptible. Either test memory word or set value. Here in this case we use a boolean called as test and set. Okay, so this will either test memory word or it will set a particular value, or swap contents of two memory words. So in this case we use a function called as void swap, which is of type which is the taking value of a pointer type of boolean. Let us see what's there in test and set code. Test and set function. This is the definition of this function test and set, where we are taking a pointer variable of type boolean as a parameter. Now we are declaring one more, a new pointer variable, that is original value, and target is equals to true, then return original value, and there is this end of test and set. Now this function always set the lock parameter to true but returns the original value of the lock. So when you apply test and set over the lock, this will return your original value of the lock, while the lock will be set to true. Now using this test and set, we are using a shared boolean variable named lock, which is initialized as false initially. Then while condition is true, we call for test and set over the lock here. While this is true, then nothing is done and critical section execution is done further. Then if lock is equals to false, after the execution of critical section here, lock will be initialized as false again, and then remainder section. And here is an end of this while loop. I hope you are getting the point. This was the thing when we call for test and set boolean function. If you're using swap function, let us see what's the code in swap function. Here we are using a temporary variable which swap the value of these pointer variables here. So temp is equals to asterisk a and asterisk a is equals to asterisk b. So we are swapping, and whatever we have assigned into temporary variable we are assigning into b. So the values of a and b are getting swapped here. Now using this swap for the solution, the shared boolean variable again is lock, which is initialized as false at the beginning. Each process has a local boolean variable key. Other than lock, a local boolean variable for each process is the variable key here. Now while the condition is true, key is assigned true. Key will be equal to true in this loop. While key is true, we are calling for this swap function along with the parameter lock and key. And then there is execution of critical section. After that, lock is assigned false, and then continued with remainder section. And this is all about the while loop. After remainder section, there is an end of this while loop. So this is how you can call for swap function. Next point is semaphores, which is an important point here. Another possible synchronization tool. A semaphore is a synchronization tool. Other than swap, test and set functions, we can call upon a semaphore, which is less complicated than the two that we discussed right now. A semaphore S is an integer variable that, apart from initialization, is accessed only through two standard atomic operations, that is wait and signal. So a semaphore is an integer variable. Other than initializing it, it can be accessed by two standard operations, that is wait and signal. So originally these operations were called as P and V, function P and function V. But we will be calling it as wait and signal operations only. Now how they are executed indivisibly, let us see. Here we have a code for wait function. So wait is applied over the semaphore S. Now in this wait function, there exists a while loop that checks the state of this S, that is semaphore. If it is less than or equal to 0, then do nothing. And semaphore is again decremented. And this situation continues. We keep on decrementing semaphore until it is less than equal to 0. If it is less than equal to, we get out of this while loop and there is an end over the wait function. We come to an end of this wait function. Then a signal operation, when it is applied over the semaphore S, it increments the value of semaphore, only incrementing the value of semaphore using signal function. While in wait function, we are checking the value of semaphore and then decrementing it. And we keep on doing this. Operating systems often distinguish between counting and binary semaphores. Now there are two types of semaphores, remember. Binary semaphore can range only between 0 and 1. Counting semaphore can have a range over unrestricted domain. So the value of counting semaphore can be 1, 2, 3 and many more. Whereas the value of binary semaphore can be either 0 or 1. On some systems, binary semaphore is known as mutex lock, mutual exclusive lock. Mutually exclusive lock it is. Mutex lock means mutually exclusive lock. Binary semaphore can be used to deal with critical section problem for multiple processes. The n processes share a semaphore mutex, which is initialized to 1. While the condition is true, we call for wait over this mutex. Remember here, mutex we are calling mutex for binary semaphore. When we call wait function over this mutex, then we execute critical section and then we call for signal over the mutex and then remainder section. So this is how we can synchronize processes using semaphores, using a binary semaphore. Now counting semaphore can be used to control access to a given resources consisting of a finite number of instances. Process synchronization can be handled with the help of binary semaphores. Whereas if you want to control the access to the given resources, you can use counting semaphores. As the resources in the system may have many instances and we need to control their access. So semaphore is initialized. In this case, semaphore is initialized to the number of resources available in the system. Each process that wish to use a resource may perform a wait function on the semaphore. And we know what happens in wait function. A decrement occurs over the semaphore. So we are decrementing the value of semaphore in wait function. So each process that wish to use a resource may perform a wait operation over the semaphore. When a process releases a resource, it performs signal operation on the semaphore, hence incrementing the semaphore value. So if a process wishes to use a resource, it performs decrement over the semaphore, indicating that one of the instance is under the usage of a process. Okay, as soon as it finishes the use of the process and releases it, it must signal it to indicate that the used resource is now again available for other other processes. When the count for the semaphore reaches 0, all the resources are in use. When the count for the semaphore is equal to 0, this means that all of the resources are in use currently, and the processes wanting to use a resource will block until the semaphore value becomes greater than 0. So if there exist some other processes that wish to use the resource, will be blocked till the time the semaphore value becomes greater than 0. Semaphores can also be used to solve various synchronization problems for concurrently running processes. Other than providing control access over the resources, it can be used as a synchronization tool for concurrently running processes as well. Let us see the implementation of semaphore. So the main disadvantage of the semaphore definition given here so far is that it requires busy waiting. The main disadvantage here for the semaphore is busy waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the entry section code. When one of the process is executing in its critical section, then any other process will be looped in its entry section, right? This semaphore implementation is called a spin lock. See, when you are using, the process who wants to enter its critical section but cannot be granted right now because other process is already executing its critical section. So this requesting process will loop continuously in its entry section, and we implement this condition using a spin lock because the process spins while waiting for the lock. Now, to overcome the need for busy waiting, we can modify the definition of wait and signal semaphore operations. We can modify their definition. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. However, rather than engaging in busy waiting, the process can block itself. Rather than continuously waiting to gain this lock over semaphore, it can block itself by executing a block operation. It block itself executing a block operation which places this requesting which places this waiting process into a waiting queue associated with the semaphore, and the state of the process is switched to the waiting state here. A process that is blocked waiting on a semaphore is restarted when some other process executes a signal operation. When this situation arises, the process is restarted by wake up operation because it was blocked, and then to resume its state, a wake up operation is executed. That changes the process from waiting state to the ready state, and it places it in the ready queue. Now here is this semaphore implementation with no busy waiting. So we are modifying the definition of semaphore here. Now type def struct, which is having, that is a structure we are defining here, having integer variable as value, and struct process list of pointer type here, and this is self-referential structure, and then you have an object to this structure as semaphore. Now each semaphore has an integer value and a list of processes. When a process must wait on a semaphore, the wait operation adds it to the list of processes. A signal operation removes one process from the list of waiting processes and awakens that process. See here, semaphore is having an integer value and a list of processes. List of processes that are waiting for this particular semaphore. Okay. And a signal operation will remove one process from the list of these waiting processes and resumes its state by invoking wake up function. I hope you have understood this point. Now see, this is the code for wait operation, wait function. Void wait semaphore S, where the S value is decremented. If S value is less than 0, then add this process to the waiting queue and block itself. In this implementation of signal function, as the signal function is called, the value over the semaphore is incremented, and we are checking the value if it is less than equal to 0. If it is less than equal to 0, the process P from the waiting queue, we remove this process from the waiting queue and calls up for a wake up operation over this process. The block operation suspends the process that invokes it. Whichever process is invoking a block operation will be suspended. The wake up operation resumes the execution of a blocked process. As soon as the process which is blocked execute a wake up operation, then it will resume its execution. These two operations would be provided by the operating system as basic system calls. Who's going to provide this operation? Obviously, operating system. Now, critical aspect of semaphores, that is, they can be executed atomically. We must guarantee that no two processes can execute the wait and signal operation on the same semaphore at the same time. We need to avoid this situation, that no two processes execute wait and signal over the same semaphore at the same time. In a single processor environment, we can solve this by simply inhibiting interrupts during the time the wait and signal operations are executed. Whereas in multiprocessor environment, interrupts must be disabled on every processor, and this can be a difficult task and can seriously diminish performance. Consequently, alternative locking such as spin lock are used instead of wait and signal here. Next point is process deadlock. The implementation of a semaphore with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused by one of the waiting process. See, here is the situation that leads to processes wait indefinitely for an event to occur. Okay, the event in question is the execution of signal operation, and this is a situation where a deadlock comes into existence. Now, to illustrate the situation of deadlock, let us see this following example. Let S and Q be two semaphores that are initialized to 1. So here we have two processes, P0 and P1, and we are having two semaphores, S and Q. Initially they are assigned value 1. Now here at time T1, P0 calls for wait over S, and at that time P1 calls for a wait over Q semaphore. See here, wait operation but on two different semaphores are invoked here by the two processes. Then at time T2, wait over Q is executed by P0 and wait over S is executed by P1. Till then, there is no problem. Then At time t3, signal is invoked, signal operation is invoked over S by P0, and signal operation is invoked over Q by P1. And then signal operation is invoked by over Q by P0, and signal operation at the same time is invoked over S semaphore by P1. So P0 executes wait over S, then P1 executes wait over Q. Then P0 executes wait over Q. It must wait until P1 executes signal over Q. See here, when P0 executes wait over Q at time T1, it must wait until P1 executes signal Q, where it is executing at this time. Similarly, when P1 executes wait over S, it must wait until P0 signals S. Since these signal operation cannot be executed, P0 and P1 are deadlocked. See here, both of the processes are not able to continue their execution. They are waiting for one another. Until P1 executes signal, P0 cannot execute further. And until P0 executes signal, P1 cannot execute further. So both of these processes are held in a situation called as deadlock, where they are not able to complete their execution, and they are waiting for each other to signal some situation here. Next point is process starvation. Another problem that is related to deadlock is indefinite blocking or starvation. Starvation, when the process is waiting for a longer duration and is not able to execute its able to continue with its execution. So this is a situation called as process starvation. Now this is a situation in which processes wait indefinitely within the semaphore. And starvation may occur if we add and remove processes from the list associated with the semaphore in a last in first out order. The starvation may occur when we add or remove the processes. In effect, processes we are adding and removing a process from the list which is associated with the semaphore in a LIFO fashion, last in first out order. Okay, so that's it for today. All of the points we have discussed here. Remaining points will discuss in the next video. Till then, take care. Thank you.